In this section, we will cover another coordinate system in three-dimensional space, so-called spherical coordinates. These are similar polar coordinates in that our first coordinate will simply be the distance from the point to the origin, but we have to deal with two angles this time instead of just one angle. This makes it a little bit more complicated than cylindrical coordinates were, and so we're going to have to do a little bit of effort to actually set this all up. So let's actually start off with a picture. We'll put in our normal rectangular coordinates, our x, y, and z. And let me get that actually through the point. Close enough. So x, y, and z. We're going to have some point out here that has its normal rectangular coordinates of x, y, and z. And then we're going to give it three coordinates, rho. This is a Greek letter that is the equivalent of an r. Theta, you should be familiar with that one. And phi. Lots of Greek letters here. Maybe I should move this a little bit so we're not actually just coinciding with the negative x-axis there. Move it a little bit over here. And I missed. Having some fun actually drawing here. Okay, so the first thing, this rho, is going to be the distance from the point, which let's go ahead and call that point P, so I can just say P to the origin. So that distance right there is rho. Theta is actually going to be an angle that we already have dealt with before. If we project this down into the xy plane, so that's just a perpendicular drop down to the xy plane, we have this line here from the origin to that point. This is what we're calling r in cylindrical coordinates. And in fact, being able to reference r is actually going to be useful in doing a number of these calculations. And then we also called this angle that this line makes with the positive x-axis theta. We're going to use the exact same theta. Let me just say same angle from cylindrical, or you can even say from polar. I mean that's where originally got theta was from polar coordinates. And go ahead and make that specify that that's a right angle there. Phi is going to be another angle, this time to try to capture how far out of the xy plane we are. But you might think, well, let's just make it this angle here, the angle in this triangle. But we're actually going to make it the angle down from the positive z-axis. This is the angle phi. Now in polar, we would sometimes allow r to become negative. Here, we could do the same thing with rho, but for the most part, nothing that we're going to be doing with this is going to require rho to be anything other than a non-negative number. Rho is only going to be 0 if we're at the origin, by the way. Everywhere else we'll have a positive rho. Theta, again, can be any angle, but normally we'll stick between 0 and 2 pi. And then phi, we could also technically have phi be any angle as well, though we'll generally stick from 0 being the positive z-axis, And then as we go around, we actually hit the negative z-axis at pi. If we try to go any further, we're actually getting other points on the other side where we can actually view them as the angles from the using different phis. So we actually the full range of all points can actually be covered by rho, theta, and phi that satisfy these conditions. And so those will kind of be our default. So a lot of the examples that we did with cylindrical coordinates and polar coordinates, we'd use theta from 0 to 2 pi if it goes all the way around the circle. This time, if we're covering everything, we'll generally have theta going from 0 to 2 pi and phi going from 0 to pi. And then rho is going to be the thing that is more often the limiting factor, where we have to actually find out the limits on rho. I should also note before we move on that the letters that we are using here are not entirely standardized. Some people swap the theta and the phi and have theta being the angle down from the z-axis, while phi is the angle in the essentially the polar angle in the xy plane. And some people will use r for what we're calling rho. We like to use rho here because it's distinct from the one that we're using for cylindrical coordinates, and that actually allows us to use the r in cylindrical coordinates in some of our formulas. That'll actually come into play a little bit as we go, especially when we're actually deriving formulas for how to get from x, y, z. We'll switch between x, y, and z to rho, theta, and phi. Another thing that sometimes happens in applications is that they will actually use this angle here, the angle in this triangle that we have drawn, as essentially the phi coordinate instead of the angle down from the z-axis. In essence, that amounts to subtracting pi over 2 from phi. One application that's actually fairly commonly used, where that's fairly commonly used, is whenever you're talking about longitude and latitude of talking about points on the surface of the Earth, because you can actually view if you had phi here, that's actually saying how far north or south you are in terms of an angle, the angle that we're making with essentially the equator plane, and then your longitude, or that's your latitude. Your longitude is telling you how far east or west you are in terms of an angle with the positive z-axis. You can say the axis of the Earth. So that's one application that we sometimes see this with. I'm not going to get too far into applications, but if you're familiar enough with those, hopefully that makes some sense. I bring up these differences here mostly because if you're trying to look up information about spherical coordinates, specifically about if you try to look them up on Wikipedia or something like that, you might find that they put them in a different format than what we're doing here. Especially since it seems like in physics they like to actually change it versus what we do in mathematics. So be careful when you're trying to look up information about this. They might be using different notation, and I'm sorry about that. Just like we did with cylindrical coordinates, one of the first things we'd like to do is look at some surfaces where we're essentially setting our different coordinates into a constant. So if we say let rho be a constant number, what kind of surface do we get? Well, keep in mind there, we're just really talking about what are the surfaces where the distance from the origin are constant. Well, those are simply going to be various spheres around the origin. I can just go ahead and even put in a whole bunch of those. So these would be the surfaces of constant rho. Specifically, the ones I've drawn are constant 1, 2, 3, 4. If you want constant theta, because we're not really considering negative rows, those will be half planes. That might be a little harder for me to only do the half planes, so I'll go ahead and do the full planes. But we might have something like x equals 0. This would actually be the plane where theta equals pi over 2. Y equals 0 is going to be the plane where theta equals 0. If we specifically wanted to only consider the half planes, then we'd actually be using this plane over here for theta equals 0, and actually the plane over here for theta equals pi. And then this one here for theta equals pi over 2, and this one over here for theta equals 3 pi over 2. Something like that. And then you have a whole range of half planes going all the way around the z-axis. Finally, for constant phi, this is a little bit more complicated. There's actually different shapes that you can get. For one thing, you could say that the positive z-axis itself is where phi equals 0. That's actually the graph of that equation, is just simply the positive z-axis. If you want to talk about, say, phi equals pi, that would be the negative z-axis. Pi equals pi over 2, or sorry, phi equals pi over 2 is actually going to be the xy plane, because those are all the points that make an angle of pi over 2, of a right angle with the positive z-axis. If you want something between those, we actually get a cone. So here I've set this up to actually show the surface of phi equals an angle. I have a slider here that will allow me to change that angle. Right now, because I have the angle set to 0, it's actually just giving me the positive z-axis, which you really can't see very well. This doesn't really show up. But as I increase that angle, we kind of fan out away from the positive z-axis and get these cones. The book is referring to these as half cones. Whether or not you want to call it half or just a cone is kind of really up to you. Some people call the ones that go all the way through and have two parts to them a double cone. So what's half, what's double, what's a regular cone? That's really not too important. But the thing here is that each of these cones is actually the graph of a constant phi. And that makes cones really nice and easy to work with in spherical coordinates. I mean, spheres already were. We already looked at these various spheres as surfaces of a constant row. So spheres are definitely easy to work with. But it turns out cones are just as easy to work with because of this fact. So as we get to pi over 2, we end up getting the xy plane. As we go further, we get down to the negative z-axis. I guess technically we could go even further than that, and it just kind of sweeps out all that again. But normally we're just going to go from 0 to pi. Next, we would like to get equations for rho, theta, and phi in terms of x, y, and z, or vice versa, whatever it can manage to do. This, of course, is not going to be entirely straightforward. It's actually going to be easier to express x, y, and z in terms of rho, theta, and phi. Really, the only one that's incredibly easy to get from the x, y, and z is rho. Rho is going to have a very nice formula for it. The other ones will have to deal with potential a trig function of that angle equals something in terms of x, y, and z. But what we're going to really work with is this triangle. So I've drawn a triangle here that makes it kind of easy to work with. So we want to be able to think about what are the things in this triangle here. Well, that's where this r comes into play. R is something we already know something about. We actually already know that r, well, should write it as x is r cosine theta, and y is r sine theta. because the r and the theta are exactly the same ones that we had for polar or cylindrical coordinates. So those are the same formulas that we had before. Can we express rho in terms of r? Well, looking at this triangle here, it shouldn't be too hard to see this angle up here on the triangle is actually the same as the phi that we have over here. Basically, this angle along with this angle, because we're in a right triangle, have to sum to be pi over 2. But of course, this angle down here along with phi is in fact just pi over 2. So those are the same angle. So if we look in this triangle here, what is the sine of this angle? The sine of this angle, basically the sine of phi, has to be the opposite, which is r, over the hypotenuse of rho. That means we can express r as rho times sine of phi. And that's actually a nice formula to keep in mind, because we'll actually make use of that fact in one of our examples. It'll just make it easier to convert our formulas between rectangular and spherical coordinates. But here, right now, what it basically does is allow us to replace the r's in our formulas for x and y with rho sine phi. Basically, x is equal to rho sine phi cosine theta, and y is equal to rho sine phi sine theta. So in fact, if we have rho, phi, and theta, we can easily get x and y just from these formulas. What about z? Well, z is actually a little bit easier, in fact, because z is actually part of this triangle. We haven't labeled it yet, but z is there. Z is just this line here. It's the distance we are from our projection down in the xy plane. And so since it's a side of our triangle, we look at trig functions of phi. So this time, we were working with sine before, so this time we look at cosine. Cosine of phi is the adjacent, that's our z that we just put in, over our hypotenuse of rho, which means that z is equal to rho times cosine of phi. And those three equations allow us to convert from rho theta phi into x, y, z fairly easily. If we want to go the other way, probably the easiest one to look at, and like I said, rho is probably the easiest one. Rho is just part of this triangle. That means that rho squared is equal to z squared plus r squared, because I mean, it's the Pythagorean theorem. But then r squared we already knew was x squared plus y squared. So you can say that rho squared is x squared plus y squared plus z squared. I mean, that's how we actually wrote our spheres before. X squared plus y squared plus z squared is equal to that distance squared. And actually, you can kind of even see that I used the formulas that we derived here in order to make these cones. So if you were wondering how I did that, I just used the fact that I knew the formulas. If you want to get get theta or phi in terms of x, y, and z, well, theta's not too bad. We actually already have a formula from polar coordinates or cylindrical coordinates that the tangent of theta is equal to y over x, and so we can just compute it that way. For phi, that's a little bit more complicated. It's actually, you can kind of think in terms of how we set this up. The sine of phi is r over rho. Cosine of phi is z over rho. In that regard, the tangent of phi is going to be, remember that's the adjacent divided by, sorry, the opposite over the adjacent. So that's going to be r divided by z. So tangent of phi is r over z. R you could find by using the fact that r is the square root of x squared plus y squared. That's probably the easiest way to write this down. There's not really any better way of doing it than that. So really, I find it really best to keep in mind that cylindrical coordinates are kind of involved here in order to actually do any sort of changing from one to the other. I mean, it's easy enough to go straight from from spherical to rectangular using these three formulas over here. But in order to go the other way, it's easy enough to kind of take a detour through cylindrical, because otherwise it's just really tricky to do. I guess if you want to just compute rho directly using x squared plus y squared plus z squared, and then use one of these formulas. So I guess cosine of phi equals z over rho. You can get away with not writing down what r is, but you have to compute rho before you can compute phi in that case. I don't know. It's just, which way do you want to go with it? We're not going to do a lot of conversion here. It's mostly we'll we'll mainly use these three formulas in order to convert things that were already in formulas that are already written in x, y, and z. We would replace them with these formulas to have a formula in terms of rho, theta, and phi. So of course, what we're really concerned about here is integration. We want to work with triple integrals using spherical coordinates, because spherical coordinates will allow us to deal with spheres a lot easier than we could in either of the other two coordinate systems we've already looked at. It'll also even allow us to work with cones even easier than we could with cylindrical coordinates, and they weren't even too bad there. They're really easy to work with here. So what we're going to do, because we can't really fall back on rectangular coordinates the way we did with cylindrical coordinates, we're instead going to have to consider the spherical version of our rectangle. So essentially we want to look at regions E, where this is going to be rho, theta, phi, where rho is between some values, let's just say A and B. Theta is between some values. I think they're using alpha and beta, because they want to stick with Greek letters. But then with phi, they for some reason switch back to using just regular Roman letters. So phi is going to be between C and D. So I've gone ahead and set up something of that form right here. So what we have right here is that kind of region E. So recall, we're basically just bounding rho by two numbers, theta by two numbers, and phi by two numbers. Here I have bounded my rho value by 2 and 3. So this is going from a radius of 2 to a radius of 3. My theta values, remember theta is the angle on the xy plane, you could say. I've gone from a theta of pi over 6 to a theta of pi over 3. And then rho is the angle down, not rho. Phi is the angle down from the positive z-axis. I've taken an angle from pi over 6 to an angle pi over 3. So this is what we're going to be calling a spherical wedge. And of course, because this is so similar to a rectangle in the form that we've written down right here, this is actually going to be the easiest thing to integrate over when it comes to spherical coordinates. And we're going to essentially take this thing and turn it into a Riemann sum. We'll essentially say if we took in a triple integral of a function over some spherical wedge, we break that spherical wedge down into a bunch of subwedges. So you could even imagine the grid lines that the GeoGebra put on here as kind of being our cuts. We basically cut it into a bunch of pieces and then look at all those various pieces as subwedges, and then basically add up all those wedges times the value of the function at some sample piece in one of those subwedges. Of course, in order to do that, we are going to have to figure out what is the volume of a spherical wedge. Or at least we are going to approximate the volume. Getting the exact volume won't matter when we take the limit. So we'll be a little bit less exact about this, but it will give us a formula that we need in order to take the integrals. So we're going to introduce essentially three variables here. Delta rho, this is going to be the difference between our b and a that are bounds on rho. Delta theta is going to be the difference between beta and alpha. And delta phi is going to be the difference between C and D. So that basically we're just looking at what is the change in rho, theta, and phi. Then we want to look back at our spherical wedge here and realize that it's not really too dissimilar from a box. I mean, we can imagine this being a box, and if we actually had smaller rho, theta, and phi, if those delta rho, delta theta, and delta phi were smaller, this would be even closer to a box. In fact, in this picture that I've drawn here, delta theta being pi over 6 and delta phi being pi over 6 is actually kind of big compared to the subwedges that we're actually going to be worried about. And even so, it still looks very box-shaped. And so we want to think about what are the actual dimensions of that box. If we imagine, say, this line right here as being one dimension of the box, then this line and that line, what are those actual distances? Well, the easiest one is the distance along here, because we're really just looking at the radial distance. That is just 2, so rho equals 2 here, rho equals 3 there, that's a distance of 1. It's actually, that distance is actually delta rho. So we can say our approximation box dimensions. The first one is just delta rho. That one's easy. The next one, this is going to be the one, you can say around here. If we're going, actually maybe, yeah. And instead, actually, maybe we should look at this one here. So kind of just, I mean, we've technically working with this one here and this one here. Those are technically two different lengths. We're of course, if our delta rho is small enough, these would actually be closer together, and so the difference between them wouldn't be too bad. But what we're essentially doing there is thinking about the arc of a circle where the radius of the circle is between 2 and 3. I mean, that's our radius here. And then the angle that's made at the origin here, at the center of the circle, is pi over 6. And so you can calculate the arc length of a circle by multiplying this central angle times the radius of the circle. So what we're going to do there is imagine that one there is the radius of the circle. Technically, this is, because we're dealing with a range of rows, this isn't really a fixed value, but in the limit, it essentially will be, times the angle that's at the center. That angle is delta phi, because that's what we're dealing with here. So we're working with the angle of phi equals pi over 6 to pi over 6 is up here. So phi equals pi over 6 down to phi equals pi over 3, and that's what's giving us the angle at the center. If we want to look at this final dimension here, this one's actually a little trickier than the other two, because this is the one that's going to involve theta in addition to both rho and phi. So here we're still kind of looking at a arc of a circle, But the actual radius of that circle is a little tricky because it's not just going to be rho. So if you look directly down at it, we could say here that we are working with the arc of a circle where the center is basically here. It's technically on the positive z-axis for what I've drawn here. And so the central angle here is going to be delta theta. But the radius, because we're not really working with something that's on down here in the xy plane, we're actually working with something that's maybe up here. We're actually going to be having a radius there of rho times sine phi. So we'll have rho times sine of phi times delta theta. Because this is it was going to play the role of the radius of that circle, and that's going to be the central angle of that little arc, and so that's the length that we're trying to use. Of course, these are kind of approximations because rho and phi are not fixed values; they're just in certain ranges. But of course, as we shrink things down, as we get into smaller and smaller subwedges, these get closer and closer as long as we pick rho in the proper pick rho and phi in the proper ranges. And that means our box volume, you can say, is approximately, if we multiply all three of these together, because that's how we find the volume of a box, we're going to have two copies of rho, so we have rho squared. We have a copy of sine of phi, but then we have delta rho, delta phi, delta theta. We're going to put those in the order of rho, theta, phi. Of course, as we pick smaller and smaller boxes, these are going to turn into d rho, d theta, d phi, like we've done before. But we get a Riemann sum, so our volume, well, actually not our volume, our triple integral. So we have some triple integral of some function f of x, y, and z dv. Well, I guess we can see it's equal if we're working with a limit. We're going to add up a whole bunch of these values well, we take a sample point. So we take a sample point xijk, yijk, and zijk. But of course, those correspond to a rho ijk, a theta ijk, and a phi ijk. We'll be summing up over all ij's and k's, whatever these subdivisions are. Technically there, because we wrote our f in terms of x, y, and z, we're going to have to replace x, y, and z in terms of rho, theta, and phi. Those go back to these formulas. X, y, and z are in terms of these. So we'll end up with a rho ijk sine of phi ijk. I'm going to completely run out of space here. Cosine of theta ijk. So that's just for x. So x ijk is this product here. For y, we have a very similar thing, except now we're going to have sine instead of cosine here. And I'm just going to have to write on the next line. And then for z, z is a little bit shorter. We have rho ijk times cosine of phi ijk. I don't have enough space here. Let me move this to the to the next page so we can actually see it a little bit better. Okay, so I've kind of just moved this over so we have a little bit more space, but we're still continuing from here over to here. And then at the end of this, now we're going to have to use our formula for the volume of that spherical wedge. So we have rho squared sine phi Of course, technically here we're going to be using our sample point, so rho ijk squared sine of phi ijk. Then we have delta rho, delta theta, delta phi. A lot of work there because a lot of it's just because we were putting in the sample points. As we take our limit, as we turn this into a triple integral, writing it as a sample point is not really useful there. There we're just replace these with rho, theta, and phi. And so that's what we get in our formula. So the triple integral of a function over that spherical wedge E, so that just written down here again, is just equal to the triple integral where we have, well, we're just using those limits for rho, theta, and phi in just on our integral signs. We have f of all of our formulas in terms of rho, theta, and phi, or rho, theta, and phi. This is just x, y, and z, just kind of written out. And then we have this, the main thing to note here is this extra factor. The rho squared sine phi is essentially it's playing the same role as the extra factor of r that we were working with in polar and cylindrical coordinates. In the last section of this chapter, we'll actually discuss what this extra factor is in more detail. But it turns out in pretty much any sort of transformation like that we're doing right here, where we're changing from rectangular coordinates to some other system of coordinates, you always get some extra factor of this form. And we'll give a formula for actually being able to figure out what that is without even having to go through all the work we've done right here of trying to figure out what is the volume of that spherical wedge. We maybe could have skipped that if we talked about those in the first place. But the main thing here is just keep in mind that anytime we're working in spherical coordinates, anytime you are actually doing a triple integral in spherical coordinates, you have to have this extra factor. Of course, here we can actually generalize this a little bit. We can look at more general regions E. There we're going to actually not change from having fixed limits for theta and phi, because it's a little trickier to actually do anything with those. Not that we couldn't, but no one really ever does. The main thing here is that we can actually change rho from being between two fixed values to being between two functions of theta and phi. So we could have something like, the book is using g1 of theta phi to g2 of theta phi. And if we do that, all that really changes is that we would change the a and the b that are here to these functions of theta and phi. But we're not really going to look at any example where we're going to have to do that. So this gets complicated enough without really having to do that, but just be aware that we can do that. And the book has a couple of examples where they do that. Or at least, I think they do at least one of them. Yeah, so their example 4 does have their limits on rho in that case were from 0 to cosine of phi. They do one example of that. But none of the examples that I'm going to do for us in these videos is going to involve anything like that, and none of the homework problems are going to involve that. And none of the test questions are either. So just be aware that we can do it, and it really doesn't change too much from the way we actually were doing it before. We're just kind of not wanting to add that extra complication on top of being able to set this up in the first place, because we had to think in these spherical coordinates, and that might be a little bit complicated to do at first, especially when we're kind of rushing through to the triple integrals. We don't. It might have been better to set these coordinate systems up in an earlier course, so we can actually get an idea of what's going on with them before we're suddenly starting to throw calculus at it. But since this video has already gone over, it's almost, I guess, actually at 40 minutes now, I'm going to go ahead and stop this video here, and we'll do example videos in a separate video. So, I'll see you in that one.